talk a little bit about superconductivity. And a lot of the stuff we're demonstrating here today is tied to what we call nanoscience. That has to do with things that are on the scales of a nanometer or hundreds of nanometers. And right now, we're going to demonstrate superconductivity, which deals with a phenomenon that is actually a factor of 10 smaller than the nanometer scale. Where the tens are hundreds of angstroms, 10 to the minus 10 meters. So first of all, I have two superconducting wafers. These are ceramic, they're a lot like a flower pot. And these particular superconductors are only superconducting at low temperature, relatively low temperature. We're going to cool it down initially with some liquid nitrogen. Okay, now, liquid nitrogen is about 70 Kelvin temperature, and which is about minus 300 and something Fahrenheit, which is pretty cold. Okay? So we got to kind of be careful with that. And so right now those superconductors are cooling down to 70 Kelvin. It's going to take a little bit. We may have to add some more nitrogen there. So now these have cooled down to 70 Kelvin, and I've got a rare earth neodymium magnet that I'm going to put on top. And you probably can all see this, and maybe afterwards I'll let you come a little closer, but for now we're keeping everybody back. Okay? So this is actually, so you can actually sit there and spin. Okay? So what's happening inside this superconducting material is, on an atomic level, we're generating currents, electrical currents, that try to cancel out the field of the magnet. Okay? And the net result is the electric field is expelled from the inside of the superconductor. And it's acting, you think of it kind of acting as like another magnet, pushing the other magnet up. Except that this is stable. You can't balance two magnets, the opposite poles of two regular magnets. You just can't do it. So it's a slightly different effect. So this is a stable effect. This is the idea behind the maglev frames. So once these currents are set up, they flow forever, as long as the temperature remains low. There's no resistance to the currents. Okay? So these little currents, we can actually demonstrate on a more macroscopic level that we're more familiar with. And to do that, we're going to need some magnets. And I got to keep my magnets separate. I'm going to have a catastrophe. These are very strong magnets, and they stick together. It's all over. So I'm gonna just move this back here for the time being. So here I have a thick wall aluminum tube. Okay? And I have another piece of aluminum. This is just a slug. I want to demonstrate that if you drop the aluminum tube, it falls very quickly, which is not
right on your foot. What? Right on his foot.
Here I have a magnet that is essentially the same size as that slug. They're going to do the same thing.
Whoa.
Okay, I'll do that again.
Do it again, Dave.
It's flowing very slowly. You almost order pizza. Time it takes. Okay? So what's happening?
Yeah.
Well, unlike the superconductor, this actually has resistance. And one of the a very fundamental physical phenomena of electricity and magnetism is that whenever you have a changing magnetic field, like a magnet dropping through a loop of wire, you can picture this as many loops of wire stacked, you induce a current in that loop. And the current, if you've ever made an electromagnet out of a nail and a wire and put it up to a battery, well, a flowing current generates a magnetic field. That's how those electromagnets work. So what happens is, as the magnet drops through these loops of wire, currents are induced. They have their own magnetic field, but it pushes in the other direction. So as this falls, it sees a magnet pushing back. And when it gets here, it sees a magnet pushing this way, but it also sees a magnet pulling on the top from the magnetic field that's involved in this magnet. So it feels both a push up and a pull up as it falls. And that's why it falls very slowly. Alright, we can demonstrate this with this as well. This is same thing going on, but this is a slightly different configuration. Again, we have a very strong magnet and a thick piece of copper. Okay? And I'm going to take the magnet and I'm going to drop it on the copper. Do that again here. Okay? This is the magnet. So if I tip it over, what do you think is going to happen if I tip it?
That's how they do it in the movies.
So this effect happens anytime you have a magnet near like a non-ferrous piece of metal, okay, like a piece of copper, brass, aluminum. It's just a question of the strength of the magnet and the thickness of the metal as to whether you can see the effect. If you take a quarter and slide it off the end, you can see it flip as it falls off. Drop it crooked, it doesn't work. And I can drop this from any height I want, and you'll see the same effect. The trick is dropping it straight.